dear Mr. Chairman. So thanks again, dear Mr. Chairman, dear Leo, for kind introduction. In fact, this presentation contains part of the work which was done more than a decade ago, and it's a continuation, logical continuation, what I did during my PhD postdoc, and now it seems that we still did not solve all the problems in the field of microstructure evolution, crystallographic texture evolution. So my talk today will be related to the assessment of deformation and annealing phenomena by various techniques, by experimental evidence and numerical approximation. So yes, this work was done together with my PhD students, Purnima Chakravarti, Janusz Bator, Vipal Dula, with whom I work. The brief outline of my talk. So first, I will talk about the assessment of dislocation density. So in order to assess the annealing phenomena, especially recrystallization, you should have a knowledge on the deformed state. Otherwise, it simply does not work. So here I will introduce some techniques how you can assess the evolution of dislocation densities by indentation, BSD, some modeling techniques. Then I will move to recrystallization, kinetics, slightly touching the crystallographic aspect of microstructure evolution, because it's again completely different topic, and only this topic would require one lecture. When we talk about the metal forming or processes or metal production or flat products, normally the material undergoes through very serious transformation, microstructural transformation. And very often we talk about so-called mesoscopic transformation during the thermomechanical processing of materials. During the mesoscopic transformation, we observe the morphology changes, like one grain, particular grain changes its shape, morphology, right? During, for instance, if we talk about flat rolled products, so rolling, it's a common technique how to reduce the thickness of the material. And suddenly when you recrystallize the material, or when you expose the material to high temperature, you see that very often this elongated microstructure, which also might fragment during the deformation, it changes the morphology again. You might get completely different type of microstructure, so equiaxed. Apart from this, you have the evolution of crystallographic texture. So it's not a coincidence that I put different colors here to this grain. So these colors might represent various crystallographic orientation. And during the deformation process, you have generation of dislocations. So you can observe it experimentally. You can study all these phenomena, deformation phenomena, experimentally, and also by employing various numerical techniques. So in order to understand the evolution of the microstructure during the deformation, first of all, we have to understand the flow of the material. Right, so very often we refer to well-established techniques such as finite element model. So it's based on the mechanical continuum, and then we have a continuum which deforms, which moves. For instance, in the we can assume that here is a rolling gap, right? This try. Okay, so this rolling, what happens in the rolling gap? We reduce the thickness of our initial material and we build up a strain inside the material. Apart from this, you have strain path change during the whole deformation process because it's not homogeneous at all. Then strain heterogeneity across the thickness due to shear. So the surface layer there subjected to shear, and therefore you will have shear, but also normal components. Therefore, the strain distribution will be very heterogeneous across the thickness. Also, roll gap plays very important role. So roll gap geometry important. We can take into account friction condition during the modeling and self-evidently properties of our material. One single drawback of the finite element modeling is the model setup and calculation time. They are time consuming. In order to set up the model, it depends on your skill, depends on the type of the model used, but it might take you, I don't know, 3-4 hours up to half a day or even more. And the calculation time, it depends on the precision what you want to get at the end. So you put 5 elements or 50 elements across the thickness, right? So therefore, very often we use symmetry for the not to model the whole thing, but half thickness, and then we can reduce. But still, it's quite a time-consuming process. Therefore, there were a lot of efforts to develop some more efficient models, and they call them flow line models, or there are also similar names. So in flow line model, basically material flows along the prescribed lines, which basically affected by the or defined by the roll gap geometry. And the hugest advantage of the flow line models is that they are very fast. They take into account strain passage, strain heterogeneity, roll gap geometry, also friction conditions, but indirectly. There is one drawback of this fitting of this model is fitting parameters. In the model which we developed almost a decade ago, there are 2 fitting parameters, and basically by this flow line model, we can almost fully reproduce the finite element results. However, still there was a question how to interpret these 2 fitting parameters. And finally, I managed to solve this problem a couple of years ago. In fact, it turned out that both of them are functions of the roll gap geometry. So R is the roll diameter, right, or radius, and mu is friction coefficient, and epsilon is the degree of the deformation. So epsilon and R, they are parameters of the roll gap geometry, and mu is a friction coefficient. Okay, here you can see the results, for instance, of the 30% deformation. So if you have initial grid, which is rectangular, so vertical lines, right? And after the 30% deformation, you have deviation from this vertical behavior due to the shear, self-evidently, right? So as you can see, the same result could be nicely reproduced with the flow line model. So this one takes couple of hours, this one takes fraction of seconds, 0.2 or 0.3 seconds. We did this exercise for many roll gap geometries, not only this one, what you can see here for different thickness reductions, different roll diameters. And as you can see, we could reproduce basically these lines you can see here. We could nicely reproduce almost all finite results. So once you have a knowledge on the deformation, amount of deformation, how it is distributed inside the material, you can move to the next stage. Somehow, okay. the next stage, how to assess the amount of dislocation. So when you deform the material, something is going on inside the material. And this something is the generation of linear defects, which we call dislocations. Here you can see the EBSD of 1050 aluminum alloy. It's a technically pure aluminum alloy, subjected to 50% thickness reduction, and all those features, what you see, basically they are created by the movement of dislocations. We observe deformation bands, deformation cells. So normally the evolution of dislocations is investigated by transmission electron microscopy, electron backscattering diffraction, X-ray line profile analysis, indentation techniques, or numerical approaches. TEM is also quite time-consuming, but also the equipment is quite complex, right? So very often people try to avoid using transmission electron microscopy if it's possible. So in my talk, I will concentrate on the EBSD X-ray line profile analysis, indentation, and other numerical approaches. Regarding X-ray line profile analysis, there are various groups who developed techniques how to assess the evolution of dislocations in various materials by observing or analyzing broadening of the line. So if you here observe, for instance, 311 line, what you observe, like after certain degree of reduction, for instance. So if you here see virgin material, so after certain degree of reduction, you will see that this line will get broader and broader. And then a group of Thomas Ungar, basically, who started this assessment a long time ago, they a group in Budapest, they developed a method how to estimate the evolution of dislocation density. So what you do X-ray measurement, and then you compare those lines which with respect to virgin one, and based on this you are able to predict the evolution of or the amount of dislocation which have evolved. Right, so what we see from the X-ray line profile analysis, that in fact with increasing the rolling reduction, the amount of dislocations tend to increase, so power 10 to 14. It's very, I would say this is the range what we typically expect to have in materials, in deformed materials subjected to 40, 50 or higher degree of straining levels, right? And then the question is to what extent these results are reliable or not. Self-evidently, you compare with the results of other researchers, so we have seen very comparable results. And then we said that, okay, let's try to estimate dislocation density by other techniques, and one of them is the indentation. So when you do micro hardness measurement, you can do it with different loads, starting typically from 10 gram force up to 2 kilogram force, right? So when you do this, you have to be aware that there is so-called indentation size effect when the hardness, in the present case, it's a Vickers hardness, is overestimated due to at lower loads. And then when you have the information about the amount of the about the hardness, right? So you always select data from the saturation zone in order to avoid this overestimation. So the group of Tony Rowett and also other groups, they developed a technique how to estimate the stored energy based on the Vickers hardness. And they proposed this simple formula where basically you need to know Taylor factor, G is a shear modulus, and alpha, what we call is a geometric constant. But this geometric constant, typically people assume that it's 0.5. However, when you do more precise calculation of this geometric constant, you will see that for the mixed screw and edge dislocations, right, this alpha tend to increase with at lower thickness reductions, right? So it might change from 0.8, and in fact, after certain degree of straining level, it saturates at 0.5, right? So for each strain increment, you can calculate the alpha. Okay, and from other side, you know that the stored energy is nothing else but alpha rho is a dislocation density GB square. When you combine these two equations, you get the new equation is this one, right? So all parameters you have HV, so this is the hardness. Alpha, you calculate, you use this either every Taylor factor 1, what you measure based on the texture. G, and B is a Burgers vector, which is also now. Then we compare the results, what we got from the indentation technique and X-ray line profile analysis. And in fact, we were quite amazed that the trend was very, very similar. And also the order of magnitude was identical. There will be always some differences between techniques, which is evident, right? So we published this work recently about the evolution of dislocations in the 1050 aluminum alloy subjected to different straining levels. And apart from this, we wanted to know whether it's possible to catch it numerically. So in fact, the total dislocation density can be modeled by original Kubin S3 model or modified version of this model, which is actually an analytical solution. So in this Kubin S3 model, you have mobile dislocations and forest dislocations and constants. Those constants were already defined for various materials. For pure aluminum, I put them here. Right, all what you need is to put these constants to this equation, and then you can easily calculate the amount of dislocation, mobile and forest dislocation. So mobile and forest dislocation, you can see their evolution, and here is the total dislocation density. By modified model, basically what people observed that C2 and C4 parameters, they are almost identical for majority of materials. And then if you assume that they are identical, you can find an analytical solution, which you can see here. And then you can directly calculate the total dislocation density inside in different materials, depending on the amount of strain. Right, so here is the results of the modeling. So Kubin S3 model, modified Kubin S3 model, so they are basically the same. And our experimental points, which were measured by hardness measurements, we observed, I would say, a really very good correlation between the model and experimentally observed data. We published this result recently. You can see them in materials characterization. So in fact, you can predict the evolution of dislocation by having information about the amount of strain which tend to develop during the rolling. Another important aspect, how those dislocations tend to evolve. So for this purpose, we did electron backscattering diffraction, EBSD, and then by kernel average misorientation. And if you have inverse pole figures and you add IQ maps, you can basically see the substructure evolution inside materials. And kernel average misorientation, if you take first or second neighbor, does not really matter. You can clearly see where those dislocations tend to concentrate. And what was very interesting to observe that at low thickness reductions, they in fact move towards the grain boundaries, and they are located along the grain boundaries. And more you increase the level of straining, then more homogeneous dislocation distribution you observe. And then you observe evolution of cells at higher straining levels, what you can see here. So the nature of deformation, grain fragmentation, the evolution of substructure can be nicely traced by the electron backscattering diffraction technique. Then another, when you calculate the kernel average misorientation, then there is a way how to calculate the amount of the geometrically necessary dislocation. So you have two types of dislocation: geometrically necessary dislocation and statistically stored dislocations, like immobiles, which are statistically stored. And GNDs, basically, they are produced by the gradients which are produced. I will try to go back. Yes, which are observed inside particular grains, right? So when you calculate the kernel average misorientation, one thing what you will immediately see is that if you put if you perform a measurement with a certain step size, then the GND what you calculate will strongly depend on the step size and the neighbor, which you choose the first neighbor, second neighbor, and so on and so further. So here we put the dependence of the GND on the so-called kernel radius, which is either step size or neighbor, right? In order to overcome this problem, Kamaya published a work in ultramicroscopy, and what was shown is that, in fact, instead of putting here misorientation, some average misorientation, you put basically this slope d theta by ds. Basically, you put the slope of, normally it's a straight line. And if you put this slope, then you get more reliable answer about the geometrically necessary dislocation. So the special care should be taken while choosing the appropriate neighbor rank or kernel radius. Another way how to estimate the amount of geometrical necessary dislocations is analyzing my tensor components. Again, here you have a very similar problem. When you have a large step size, like Burger's, think of Burger's circuit here, right? Most of the dislocations within the circuit will interact with the dislocation of opposite signs. So if your step size is too large, like here and here, you will miss these two dislocations. When you have too small step size, then you will run into another type of problem, which is called noise. So you will have overestimation of GND density. In fact, this problem was observed almost 2 decades ago by and published by David Field and co-authors. What they show that, in fact, you have overestimation or noise at very small step sizes and underestimation at large step sizes. And then the question is, what should be the appropriate step size? So the appropriate step size should be comparable to the length scale of the dislocation cell structure, right? And then the question is, how can we estimate the size of the cell structure? When you look at the what I call classical works, it's work of Gilles Severiano and co-authors, published again in 1980, where they summarize the evolution of the subcells with strains. For instance, in aluminum alloys, I took this data, and then I draw a line, and basically now I have I put all the coefficients to this equation, which I derived for this curve, right? And I can immediately calculate the cell size. Once I know the cell size for various strains, based on this, I can define the step size for my measurement. Look at the results of our measurements. So if you work with a constant step size, for instance, 0.6 micrometers, here you see those triangles, right? And then you have GND estimated by kernel average misorientation. So completely different behavior. In one case, it's tend to drop. In another case, it's tend to increase. However, when we use, when we calculated the GNDs with the step size or Kellner radius, which was comparable to the cell size, we obtained almost identical results with those which we observed by this kernel average misorientation. And in fact, it's physically sound the amount of GND tend to increase with the straining level. And what was very interesting to observe that almost half of them, this line tend to saturate at almost 0.5, 0.48, something like that, right? So almost half of the dislocations which are generated, they are GNDs. The rest are trapped. So 50% will be trapped, and we call them statistically stored dislocations. So here you have also from the model, mobile dislocations and forest dislocations. They are, I would call, upper and lower bounds. Again, once you know the dislocation density, you can easily calculate the stored energy or energy which is stored during the plastic deformation. Here you have the simple formula, alpha rho GB squared. So rho you either estimate by the model or by indentation or by other techniques, or simply you take GNDs from EBSD, you multiply it roughly by 2, it will also give you a very good guess, right? But not at very small levels, like after 30–40% thickness reduction, we observe this saturation, right? Okay, and here is our Kubi-Nestin or modified Kubi-Nestin model. So we calculated the stored energy, right, by the model, putting rho which comes from model, and then again by the indentation, again we observed quite good correspondence. And then I looked at the papers which were published almost 2 decades ago, work of Huang and Humphreys, where they estimated the stored energy in aluminum alloys, right? Also in almost pure aluminum alloys. And I was amazed that in fact, those are our results, what we have seen. So based purely on GND, what we measure by EBSD, and that's the results of the work of Humphreys. In fact, by EBSD, we nicely revealed the GND, and in fact, those points for what they I mean, the amount of stored energy which they have estimated, they nicely correlate with the results which we also observed in our alloys. So it seems to be that those techniques are quite reliable. Now, talking about the crystallographic aspect of microstructure evolution during recrystallization, you should know that in FCC materials, when they are subjected to rolling, a specific fiber tend to evolve. It's a complex shaped fiber, this what we call beta fiber. It looks like this inhaler space, right? And for many years, there was no precise description of this fiber, and almost 10 years ago, we managed to found the analytical description of this fiber, and basically by this massive formula, you can describe all components of this skeletal line which you observe in space. Right, normally it's copper component. People also refer to S component, which is in between the copper and brass component, right? So here is the copper, here is brass, here is S component. And what is very interesting that when you recrystallize this material with this type of texture, this texture is completely changed. So instead of having this beta fiber, this will transform to completely different fibers. You have this Q fiber, or what we call theta fiber. You have alpha fiber components like gauze, some P component sometimes, and in some instances you also have very big gamma fiber components, but that's due to the presence of particles which you normally have in aluminum alloys. Okay, then in order to understand the evolution of crystallographic texture, we developed a model which allows us to predict the evolution of crystallographic texture during recrystallization based on the deformation texture. If you remember at the beginning, I told that we should have very good knowledge about the deformed structure. So in fact, when you model the recrystallization texture, you should have very good knowledge about the deformed state. So we take deformation texture, then we apply gross enucleation operators on this gross texture. So gross operator in our case is micro gross selection. We assign high mobility to 1, 1, 1, 40 degree oriented grains with respect to the deformed structure, right? And then we apply so-called orientation selection or nucleation operator, which implies that you employ low stored energy nucleation. So only those nuclei with the lowest possible energy will grow. In fact, physically, it's sound because system tries to reduce its stored energy, and only those nuclei will grow which have lowest possible energy. So the results of this work were published in a couple of journals in IGP, Acta Material, and so on. And our model was based on the previous models, which was developed by Engler, also Kestens, work of Kestens and Jonas. And regarding particles, we took the knowledge from the group of Humphreys. So when you have particles, then you have particle affected deformation zone, and then you have PSN particle stimulated nucleation, which in fact compete with the bulk nucleation. Right, so how about a couple of words about the performance of these models. In fact, we can nicely reproduce experimental textures after when we had different hot bands, we subjected this initial texture to different straining levels. We got different recrystallization textures. So here experimentally observed recrystallization textures, and one which we could reproduce by our recrystallization model. So major components could be nicely reproduced. So it was done for 6016 alloy, and then also we did this for 5182 alloy. This was special alloy because it contained a lot of particles. So PSN particle stimulated the nucleation was prevailing in this case. And at lower thickness reductions, like 74%, we had quite continuous theta fiber. And then by increasing the rolling reduction and subsequent recrystallization, we observed concentration of this concentration of rotated cube texture components, right? We see two strong peaks here in 45, again in 90 degree section. And it could be very nicely reproduced by our recrystallization model. So In fact, this model works. There is one drawback. The model does not include any kinetics. So therefore, it's important to study the kinetics of recrystallization. Normally, the kinetics of recrystallization is addressed by the well-known Johnson-Kolmogorov equation, which is almost 100 years old equation. However, we still did not resolve all problems with this equation, and I will explain you why. So there are a couple of model parameters like B parameter and N parameter. We can say that they are material related parameters. Yes, that's true. However, you want to understand how to calculate or how to estimate this B and N parameters. So fraction of recrystallized grains basically depends on two model parameters B and N, and here you have time. Right, so these model parameters B and N, they are complex functions of microstructural features which tend to evolve during deformation. Thermomechanical process parameters and chemical composition, which means that for different chemical concepts, you will have different B and N values. Well, later on, scientists developed various techniques, and they managed to resolve a couple of problems. So it turned out that B constant or B model parameter, it's a function of so-called shape factor, which is a constant. Okay, then you have growth rate here and nucleation rate. And let's start with the growth rate. Growth rate is nothing else as the mobility of the grain boundary multiplied by the stored energy. Okay, I talked a lot about stored energy. At least we have quite reliable techniques how to estimate the stored energy. And then the mobility you can calculate by this simple expression, right? So you should know the activation energy, temperature, you know. So if you put, for instance, those parameters to your equations, you can calculate the mobility. At least we can calculate GB. Okay, FB now it's a shape factor, that's okay. And then the question is how to calculate the nucleation rate N. Okay, N in fact is defined as N0. Here you have the surface energy of grain boundaries, Burger's vector, it's constant temperature. You know, K is constant, okay, it's a Boltzmann constant. And however, the nucleation rate depends on the strain, right? So sometimes people multiply it with strain or strain rate, or they use some normalized values. Okay, in our analysis, we simply multiply it by strain. But the question is how to calculate this N0. Then I came back to our recrystallization model, which we developed more than a decade ago, right? So I started to analyze the outputs of our recrystallization model. So if you have a deformed matrix, assuming represented by 2000 crystals, so deformation texture, then in the model we calculate so-called gross potential texture. So we generate potential nuclei, right? So we have 8 variants instead of 2000 crystals. We will have immediately 16,000 crystals, so 8 potential nuclei per deformed grain. However, when you apply nucleation operators, so I will end up with approximately 3,500 grains. So it depends from case to case. So roughly 1.7, I would say 2 nuclei per deformed grain. So with this approach, we were able to reproduce our recrystallization texture, right? We have this selection only 2 out of 8 due to low stored energy nucleation. So some grain, it depends on the orientation. Some grains they will produce more nuclei and others less, but on average 2. However, the formation of the grain assembly is heterogeneous, so you have not only one strain mode internally, you have always more, especially if you have particle effect deformation. So then you have at least another 3 strain modes. If you have deformation bands or shear bands or whatever, so sometimes you have, so then even the most homogeneous strain mode, macroscopic strain mode, internally will be accommodated completely differently. So instead of one strain mode, you will have more. So sometimes you might have 4 or more nuclei, so you have to double or even triple the amount of nuclei due to these different strain modes. Okay, so on average, I say that one grain might produce approximately 5 nuclei. What you can also do, you can calculate the incubation period for the recrystallization. So it depends on the gamma surface energy. There is stored energy, C is a constant, about 2.5. Then radius of the nuclei, which is also constant, approximately 2.5 micrometers. Then mobility, you know, stored energy, you know. So it's strain and temperature dependent, but I calculated for our cases, it was between 0.5 and 2 seconds for high temperatures like 500 centigrade or even higher. So if you have a grain, initial grain, with the average grain size of 27 micrometer, I calculated the volume, so the volume of initial grain and deformed will be identical, and then assume that this grain will produce me 5 nuclei, right, within this period. 0.5 or up to 2 seconds. Then I get nucleation rate. I put all these parameters here, right? So then I get nucleation of 10 to the power 14, 10 to the power 15, right? So N0, I calculate back. If I know the N, I can estimate the N0. And it turned out that in fact, N0 is approximately 10 to the power 15 for 550 centigrades and strain E equals 0.70. In fact, we have checked literature sources which are claiming that in fact one grain can produce 3-4 nuclei. So I based my assumption on this. Good. So at least we have order of magnitude for N0. Then another parameter which we still do not know is N. Rami constant. And this is the most difficult parameter to estimate because at least the rest you can calculate somehow. And this one, there is, for the time being, there is no way. In the original GMAC analysis, it assumed that we have nuclei which are randomly distributed. For this case, N is equal to 0. However, you never have this random nucleation. So N constant, the GV constant, however, you hardly observe this. You observe it for small strains and also fine grained materials, then it might be true, but for the rest of the cases, it's not. Normally, what scientists claim that in fact N is between 3 and 4 when the nucleation rate is time dependent, and in fact N tends to drop during the recrystallization process with time, right? So then in this analysis, N is tends to vary between 3 and 4. Normally, when N drops fast, all nucleation events occur at the beginning of recrystallization, and these kinetics can be described with N, which is close to 3. That's what we know from various literature sources. Then grains are constrained by microstructural constraints. So when the grain can go in one direction or 2 directions, for instance, you have columnar grains, or when it grows only in 2 directions, right? And also will deviate from this ideal case, it won't be 4. So the question is which one to choose. Then various groups, those are, I would say, those are earlier investigations in 60s, 70s. Then later investigation group of like Stefan Zafferer and co-authors, they published a paper in 2001 in Acta Materialia where they investigated iron-nickel alloy with the grain size of 10 micrometer. And then it turned out that N is very close to 1, or was varying between 1 and 1.5. Then a group of sellers, basically in 1980s, they claimed that N is not constant and tend to drop during the recrystallization process. Davis Hutchinson in 1989, what he claimed that in fact in fine-grained copper and coarse-grained copper, N was varying. So for the same material, identical conditions. However, only the thing what was different is once worked with fine-grained material, in other case, coarse-grained material. So this N seems to be sensitive to microstructural features. Very similar work was done again by a group of sellers in 80s, late 70s in stainless steels. So in more fine-grained materials, they observed N, which was equal to 2, and when the grain size increased, so coarse-grained material, N was equal to 1. So in fact, there are more questions than answers. And then, in fact, Tony Rowlett and co-authors, they did simulations of GMAC theory, right? So what they claim that larger grains have a less preferential nucleation site and or less stored energy, and then they recrystallize at lower rate compared to finer grains. However, we also have to take into account that if you have very coarse microstructure, they tend to develop shear bands. There is also a famous paper of Davis Hutchinson, right? So, and if you have shear bands, then the whole recrystallization kinetics will speed up. For the time being, we leave this parameter, N parameter, as a fitting parameter in the model. And then in our investigation in 1050 alloy, we worked with 1050 alloy because it's technically pure aluminum. We wanted to work with idealized system. So 350 centigrades, right, recrystallization, and after various training levels, 36%, 46%, and 54% thickness reduction by rolling. So we calculated here our experimental data, right? And then we set N0, which was fixed for all cases. So if you remember, I told you the approximate value was 10 to the power of 15. So for all cases, in our case, the ideal parameter was 2.87, 10 to the power of 15. And then we managed to reproduce this kinetics with N equals to 2.5. That was one parameter, one model parameter. Then we go further. The same condition, but recrystallization occurred at 450. Still, we were able to nicely reproduce the kinetics of recrystallization, and we were quite happy to see this. Seems to be that we can nicely model all parameters, we can calculate them, and we can do reliable prediction until the moment when we performed annealing at 550 centimeters. Then suddenly, at small thickness reduction, it worked perfectly. However, at larger thickness reductions like 44 and 55%, and tend to drop to 2.2, 195, which means the whole recrystallization is more sluggish compared to other cases. And then we analyzed again earlier papers from 70s, work of Holm and Hornbogen. What they claim that in fact higher degree of deformation and high temperature accelerate the formation of aluminum iron particles in similar systems. Right? They did a lot of TM work, and therefore N tends to drop. In fact, when you have higher straining levels, right? So the formation of precipitation is more likely here, and therefore, in fact, these precipitates will slow down the recrystallization, therefore, and tends to drop. So you have to take into account all these microstructural features. Summarizing my work and my presentation, I would like to say that, in fact, the evolution of dislocation density during cold rolling can be traced either by X-ray line profile analysis or micro indentation. Both provides comparable values, as you have seen. However, indentation, what we have observed, tend to overestimate the quantity of dislocation at very low deformation levels. Then you can also calculate the evolution of, or simulate the evolution of dislocation density by numerical approaches like Kubinestrin model or similar approaches. There is also model, very similar model of Frederick Barla, published in International Journal of Plasticity, as far as I remember. Then when you calculate the GND from EBSD, you have to be aware of the kernel radius, right? It should be comparable, or the step size of the scan should be comparable to the size of the substructure which evolves during the deformation. And then based on these quantities, you can basically discriminate between statistically stored dislocations and geometrically necessary dislocations. Regarding recrystallization modeling, in fact, what we have seen that many parameters can be derived like this. If you know dislocation density, you can calculate the stored energy, you can calculate the mobility, right? If you know the mobility, then you know the growth rate. The nucleation rate seems to be working okay now, more or less you can guess. The problem is still what we see is the with the Avrami exponent, which seems to be a complex function of many microstructural features, right? And with this, I would like to thank you very much for your attention, and I will be very happy to answer any of your questions.
Thank you, Jurij. Thank you. Our applause for you. And so I will stop the recording here. Okay, stop recording.